Okay, in this class we will discuss some of the important problems which is based on the knuckle joint. We know that last class we discussed regarding that the brief introduction regarding that knuckle joint, where we will use that knuckle joint. As we all know that joint is used to connect two rods or bars when a small amount of flexibility or angular movements are required. Okay, so in that particular cases we will use this type of joint. So apart from that, okay, some of the major components which are present in this knuckle joint, so the collar, taper pin, the fork, rod and high. Okay, so the design of high and design of knuckle pin, we discussed all these things in the last class. Okay, now with respect to this given problem, first let us understood the given problem. So the problem is the design of knuckle joint to transmit 150 kilonewton. The design stresses may be taken as 75 Newton per mm square in tension, 60 Newton per mm square in shear and 130 Newton per mm square in compression. Okay, so this is the given problem. So with respect to this, we need to design we need to design the rod. Next we need to design the knuckle pin and collar. Next we need to design of eye, design of fork. These are the four important parameters we need to discuss with respect to this given problem. First, let us note down the given data. The given data with respect to this problem is, here we have a which is transmit at a load, that is 150 kilonewton. Okay, next we have the stresses, the tensile stresses which is 75 Newton per mm square, shear stress 60 Newton per mm square, and the crushing is 130, which is 130 Newton per mm square. 130 Newton per mm square. Okay, now first parameter, first we need to design with respect to this knuckle joint. First we need to design of rod and rod end. So with respect to this, first what we need to do, as we all know that the tensile stress in the rod, so sigma T is equal to 4F divided by pi d square. We know that the equation which is available in the design data handbook, the equation number 17.46. So if you substitute all the values into this equation, we know the sigma T which is given in the problem, that is 75 Newton per mm square. 75 into 4 into F is equal to 150 kilonewton, that 150 into 10 to the power 3 newtons, okay, divided by pi d square. We need to find out the diameter of the rod. Diameter of the rod D is equal to, if we simplify this, we'll get 50.46 mm. 50.46 mm. Say the standard diameter is equal to 52 mm. The standard diameter D is equal to 52 mm. So next what we need to find out, we know that the diameter of the rod end. So the diameter of the rod we need to find out the diameter of the rod end as per the design procedure. So next we need to find out diameter of the rod end. So that is the D1 is equal to 1.2 D. D1 is equal to 1.2 D. We know the value of D, that is 52 mm. So 1.2 into 52. If we simplify that, D1 is equal to, we'll get 62.4 mm. So that is equal to 64 or 65 mm. So we'll make it the standard value. We'll round up this value to this standard value, that is called the diameter D. Okay, the design of rod and rod end. So this is the rod and rod end. So with respect to this, D1 is equal to 65 mm. D1 is equal to 65 mm. So next what we need to find out? So we need to go for the second parameter, the second component, that is the design of knuckle pin and collar. Knuckle pin and collar. So here we need to assume the bending of the pin is prevented by the selection of proper fit. Okay, so we can assume that we can prevent that, okay, the bending of pin, okay, by selection of the proper fit. Okay, next with respect to this, we need to find out the diameter of knuckle pin. The diameter of the knuckle pin, D2 is equal to D, that is equal to 52 mm. So the diameter of the knuckle pin 52 mm. Next parameter, the diameter of the pin head. So that is equal to diameter of collar. So D3 is equal to 1.5 D. So if you substitute that value, 1.5 into D is equal to 52, we'll get D3 is equal to 78 mm. We'll make it that value to 80 mm. That is the standard value, the diameter of the knuckle pin head or the diameter of the collar. Next we need to find out the thickness of the pin head. Thickness of the pin head is equal to thickness of collar. So H is equal to 0.5 D. So you need to remember all these things. 0.5 into 52 will get 26 mm. The next parameter as knuckle pin is subjected to double shear. Knuckle pin is subjected to double shear. Okay, the shear strength of knuckle pin F is equal to 2 into 5 by 4 d2 square into tau. So this is the equation which is available in the design data handbook, the equation number 17.53. okay, the equation number 17.53. if we substitute all the values, so we know the value of, okay, the 2 2 into, we know the value of, okay, f. So we can write like this. Okay, this equation we can write like this: tau is equal to 2 into f divided by pi d2 square. So if you substitute all the values, that is 2 into 150 into 10 to the power 3 divided by pi into d2. We know the value of d2, that is 52 square. So if we simplify this, we'll get 35.315, which is Newton per mm square. So which is less than 60 Newton per mm square. Okay, which is less than 60 Newton per mm square. Okay, so here the shear strength of the knuckle pin, so which is less than the allowable shear strength. Okay, so here as the induced shear stress in the knuckle pin is less than the allowable or permissible or design stress, the design of knuckle pin is safe. The design of knuckle pin is safe. Okay, so next we need to go for the tearing strength. Okay, the tearing resistance or the strength of two sections across the fork, that is equal to F is equal to 2a1 d1 sigma t. So where a is equal to a1 is equal to 0.6 d. So we know the value of t, 0.6 into 52. If we simplify that, we'll get 31.2 mm. So if we substitute all the values into this equation, so if we substitute the value of a into this equation, we know the value of f, that is 150 Newton, 150 into 10 to the power 3 newtons, that is 2 into 31.2 into, we know the value of d1, that is 65. We know the value of sigma t, that is 75. So if you simplify this, we'll get 304.2 kilonewton, so which is greater than 150 kilonewton. So which is greater than 150 kilonewton. So here as the resistance is greater than the force transmitted, then design is safe. Okay, next the diameter diameter of knuckle pin, d2 is equal to 52 mm. Diameter of the knuckle pin d2 is equal to 52 mm. So here, so this is about the design of knuckle pin and the collar. Next, the third parameter is the design of eye. Okay, so here first we need to find out the thickness, diameter, and next we need to find out the shearing strength. So with respect to that, we can find out the the shearing strength. Okay, so design of eye. So with respect to this, we need to find out the thickness of eye, that is B is equal to 1.25D. So that is equal to 1.25 into D is equal to 52. So we'll get B is equal to 65 mm. B is equal to 65 mm. Next, what we need to find out? We need to determine the value of D, the diameter of eye. Diameter of eye, that is D4. D4 is equal to 2D. So we know the value of D, that is 52. If we simplify that, D4 is equal to 104 mm. D4 is equal to 104 mm. D4 is equal to 104 mm. Next we need to find out that the shearing strength. Third parameter with respect to this, the design of eye. The shear strength of eye. So that is equal to F is equal to tau B D4 minus D2. D4 minus D2. So here shear strength or shear stress induced in the eye, that is equal to tau is equal to F divided by B into D4 minus D2. This equation, which is available in the design data handbook, the equation number 17.48. So with respect to this, if we substitute all the values into this equation, we know the value of F 150 into 10 to the power 3 Newton divided by, we know the value of B, that is 65, into we know the value of D4, that is the diameter of eye 104 mm, minus we know the value of D2, that is 52. So if we simplify this, we'll get 44.4 Newton per mm square, so which is less than 60 Newton per mm square. So here it is also less, then the design is safe. Next parameter with respect to this design of eye, we need to find out the tearing strength. The tearing strength of eye, that is F is equal to sigma T B D4 minus D2. We know that the tensile stress induced in the eye, that is sigma T is equal to F divided by B into D4 minus D2. So this is also which is available in the design data handbook, that is equation number 17.47. So we know the value of F, So that is 150 into 10 to the power 3 divided by, we know the value of B, that is 65, into, we know the value of D4, 104 minus 52. Okay, if we simplify this entire term, we'll get 44.4. Okay, we'll get 44.4 Newton per mm square, so which is less than 75 Newton per mm square, which is given in the problem. Okay, then the design is safe. Okay, the allowable permissible stresses. Okay, so allowable tensile stresses which is less than that. Okay, so then design is safe. Next, what we need to find out? We need to find out that crushing strength. We need to find out the crushing strength. Crushing strength of high is equal, sigma c is equal to f by d2b. So this is available in the design data handbook, the equation number 17.51. Equation number 17.51. If we substitute all the values into this equation, we know that f is equal to 150 into 10 to the power 3 divided by, we know the value of d2, 52 into b, so that is 65. So we'll get 44.4 Newton per mm square, which is less than 130 Newton per mm square. Okay, so here if you compare that, all the, okay, the induced shear, induced crushing stress in the, okay, high is less than the allowable or permissible, okay, the stresses. Here also which is less than that. Okay, here also which is less than that. So with respect to this, the design is safe. Okay, the design of I is safe. Okay, next we need to, okay, we need to write a comment with respect to all these, okay, all these. So induced stresses in shear, tension and crushing are less than the permissible or design stresses, then the design of high is safe. Okay, the design of I is safe because, okay, here also which is less than that. Okay, here also the induced stresses are less than that, here also which is less than that, so then the design is safe. So next parameter we need to go for the design of fork. Okay, the design of fork. Design of fork. So first parameter, thickness of fork. A is equal to 0.75 D, so that is equal to 0.75 into 52, so we'll get A is equal to 39 mm. So I'll make it the standard value. A is equal to 40 mm. A is equal to 40 mm. Okay, the next, the shear strength. The shear strength or shear stress induced in the fork. So which is F is equal to 2a tau d4 minus d2. This is the equation. Okay, so we can also write like this: the shear stress induced in the fork, that is tau is equal to F divided by 2a d4 minus d2. So with respect to this also we need to check all the shear stress, tensile stress and crushing stress. So then we need to conclude that either design is safe or fail. Okay, so this is available in the design data handbook, the equation number 17.50. So substitute all the values with respect to this given equation. We know the value of F 150 into 10 to the power 3 Newton divided by 2 into, we know the value of A. So A is equal to 40 mm into, so we know the value of D4. D4 is equal to 104 minus D2 is equal to 52. So if we simplify this, we'll get 36.06 Newton per mm square. 36.06 Newton per mm square. So which is less than 60 Newton per mm square. Okay. Next we need to go for that the tearing strength. The tearing strength of fork. So F is equal to 2a d4 minus d2 into sigma t. So we know that tensile stresses induced in the fork. So sigma t is equal to F divided by 2a into d4 minus d2, which is available in the design data handbook, that is 17.49. So if you substitute all the values, substitute F is equal to 150 into 10 to the power 3 divided by 2 into, we know the value of A, that is 40, into, we know the value of D4, 104 minus D2 is 52. If we simplify this, we'll get 36.06 Newton per mm square. So which is also less than 75 Newton per mm square. 75 Newton per mm square. Okay. Next, what we need to find out? We need to find out the value of the crushing stresses. Okay, the crushing strength. The crushing strength of fork. So F is equal to 2a d2 sigma c. So we know that the compressive stresses induced in the fork, compressive stresses induced in the fork, that is sigma c is equal to F divided by 2a d2. So this is available in the design data handbook 17.52. So if you substitute all the values, so 150 into 10 to the power 3 divided by 2 into